This is Emily Pham presenting her lab report 2. The purpose of this lab was to investigate the motion of an object falling slowly from rest. In particular, the velocity and position of the object will be observed using an experimental and 2 computational models. The main physics principle used is the Newton's second law, which states that the change of momentum of an object is equal to the net forces acting upon said object during a certain period of time, and it will be denoted using the equation F equals ma. The integrations of this are the velocity and position update formulas, which will be used in the coding aspect, and average velocity equation will also be used. The equations for each of the forces found during this lab will be the force of gravity and the force of drag, which are also shown on the left. This is the main preview of our lab and the final results of this lab. The 2 models are an experimental model and a computational model, further explained later in this slide. The experiment is where a loosely crumpled piece of paper was dropped from rest, and then this video was then imported onto Tracker and calibrated as described. This object was then tracked using the tracking tool at each frame of the video. The coding aspect has the crumpled paper ball as the system, and the surroundings being the Earth exerting a gravitational force and the air exerting a drag force. The initial conditions are as stated, with a note being a lot of the information being taken from the Tracker video, and then the specific coding with each model will be with drag and without drag. For without drag, the proportionality constant of drag force is set to 0. The gravitational force would be the only force, and thus the net force. And acceleration was found using Newton's second law, dividing the net force by mass. And then acceleration was input into the velocity update formula, and then velocity was input into the position update formula, and it was then incrementally done at each time step. This is able to be used since the time steps are so small that acceleration does not need to be accounted for in the position update formula. Then with drag, the same thing is essentially done, with the differences being proportionality constant being set to a number, and the net force being the sum of the gravitational and drag force, since there are multiple forces present. In conclusion, there's very little similarities between the experimental model and the computational model and without drag, while the experimental model and the computational model with drag are nearly identical. This is because in real life, there are multiple forces acting besides only gravity, since we are not in a vacuum, and thus there's going to be changes in the net force as the drag force is increasing with the increase in speed as the object falls. This would then result in the results seen as they reach equilibrium, with the speed decreasing, with the speed leveling off rather, as time passes. Additional questions: what does this mean? The leveled off speed would be the terminal velocity, since it depicts the velocity graph beginning to level off, and that is shown in the computational model with drag. This system approaching terminal velocity means it's also approaching a net force of 0, which means that there's no more acceleration occurring and thus no more changes in velocity. And what if the system was initially thrown downwards? The terminal velocity would be about the same, since the drag force would need to be the same as the gravitational force, which means that the velocity would also need to be the same as the previously shown terminal velocity. And this is further shown as this model, where I changed the initial velocity to be -5 meters per second rather than the initial 1 point something velocity. And this still levels off at around the same point of around 2.5 or a little bit over 2.5 meters per second.